into account implicit consumption traits of the user rather than explicit search terms being provided as would be done in search engines. And so you discriminate between two areas of computer science. One is information retrieval, which is essentially all the search engines like Google and Yahoo and so on. And then, of course, information filtering, where we are looking at building recommender systems where you don't have to give a search term. You're actually presented with content that you are interested in without having to ask for it explicitly. Now, when we look at the space of recommender systems, there are essentially two different schools of thought or two different approaches to building these recommender systems. One of these is called content-based filtering. So what you're doing here is every individual user is tracked in terms of what they're consuming, and then recommended items that are similar to what have been consumed in the past. The disadvantage of these systems is the fact that typically what gets recommended is very similar to what has been consumed in the past, and so there's very low diversity in the recommendations that are produced. So if you go to a news website that's only doing content-based filtering, and say it just so happens that the first day the World Cup of cricket is going on, and so you end up consuming only news about the World Cup and run out of time and then therefore leave the website. The next time you come along, you're only going to be recommended stories to do with cricket, even though you might be interested in politics as well. The other important thing to recognize is that content-based filtering requires some kind of description of the item. And these descriptions can be quite complex, right? So if we look at movies, for example, there's a structure to it in terms of the fact that it belongs to a particular genre, the title of the movie, there's a plot that's described. You have actors that act in those movies, the director, the cinematographer, so the whole crew that was involved in actually creating the movie. And now the question is, how do I actually compare one movie with another, right? So how do I calculate similarity here as well? And that can be a complex kind of graph problem. So the alternative to content-based filtering is this idea of collaborative filtering, where you're tracking all users, and you've got your user UA, which is your active user here, and you of course have another bunch of other users that are consuming content, and this is the set of users U. And what you're doing as a form of a recommendation is that you're identifying certain individuals within the user base that are actually similar to this user in terms of the content that they may have consumed, right? So maybe you decide that these three users are what is called in the neighborhood of user A. And now, if there are movies that have been consumed by users in the neighborhood that have not been consumed by UA, those would get recommended to UA, right? And so there is kind of this crowdsourcing that's happening of information, and we're using that to make recommendations. One of the advantages of collaborative filtering is that this can work, firstly, without any item descriptions. And we'll see how that works without item descriptions in a second. Also, what happens is that there is more serendipity, right? So you can get very unusual recommendations. So you might have watched a number of science fiction movies, but you might actually get a movie that is a thriller being recommended to you, only because people in the user base that are in your neighborhood have watched a lot of science fiction, but a large number or large proportion of those have also watched science, in addition to science fiction, they've also watched thrillers, right? And so you actually start getting recommended movies outside the genre that you've actually watched in the past. And this initial research in collaborative filtering was done in the University of Minnesota, where a professor, John Riddle, and his group called Group Lens, it's John Riddle, if you're looking that up, in 1994 came up with the first collaborative filtering algorithm. Right, and so what they did there was essentially build up this concept of defining similarity between users and being able to recommend based on previous consumption patterns of other users. Now, while it solved the problem of low diversity that content-based filtering had, it also created new issues, right? So one of the big problems with collaborative filtering is the fact that if, like I said, the movies that are recommended to UA are only movies that have been consumed by his neighborhood, then when a new movie comes along, which is called the new item problem, what happens here is that nobody has actually rated it or consumed it, right? And so it cannot be recommended by a collaborative filtering algorithm. Similarly, if a user has not consumed any movies already, then you can't really recommend to them because there's no way to calculate a similarity between users, because essentially a user is defined by a vector of ratings for movies or items. I'm using movies as an example here. Of course, collaborative filtering is used in other domains too, and I'll talk about some of those domains. But essentially, you also have the new user problem, right? And these are both big problems for retailers, because for a retailer, new items being introduced into the catalog is very important. It's the lifeblood for the business, because that's the way you can actually get existing users to consume more. And if you can't recommend them, then that's a problem. And similarly, of course, acquiring new customers, just as ATG is doing right now by running this webinar series. How do you actually acquire new customers if you can't give them good recommendations from the moment they join? And so typically what is done is we create hybrid algorithms that utilize the best of content-based filtering, but also incorporate some collaborative filtering within it. And this is a general trend in machine learning, that you would actually end up with these algorithms that are ensembles of different models. So you wouldn't really use only one approach in solving a problem. So let's look at some of the types of problems that we have solved using recommender systems within Tatras, which is the company I founded when I moved back to India in 2012. And one of the early problems that we were faced with was this whole idea of matching job applicants with job opportunities, right? And what we built here was what is called an applicant reciprocal recommender, which comes from the idea of dating sites, right, where you have people creating their profiles, and when you're trying to recommend one profile to another person, then we are looking to not only check whether the active user is a good match with this profile in terms of what their desirable features are of a partner that they would meet. It's also looking at the other user that is about to be recommended to the active user, and seeing whether the active user actually matches their ideal partner as well. Right? And so what we were doing here was to say, well, it's not just about the candidate having the skills to fulfill the job role that has been advertised, but does the organization that's advertising the job have the right culture and the mix that would actually be ideal for the candidate, right? So if a candidate has always worked in multinational companies, is he really going to fit into, or she going to fit into the startup that is advertising this job? So skills in itself is not enough. And then another area that we worked on, which I brought out here because it doesn't really fit into collaborative filtering or some content-based filtering, is this idea of social recommendations. So there was a startup in India that was developing a platform similar to Pinterest, where you can essentially look at design ideas or ideas in general and pin them to boards, collecting some kind of ideas within the social network. And the recommender system that we built there used something that I'm not going to have time to go into today, but essentially a bipartite graph where you had pins and boards, and this graph is then traversed using a random walk to come up with recommenders, right? So this is just to give you a flavor of the fact that every recommender system that we have built really, and in machine learning also, there are always some nuances of the actual problem that you're trying to solve. And so just an algorithm out of the box is not going to work for your problem. Another area that we have used recommendation technologies in is adaptive learning, right? So you all probably are familiar with MOOCs like Coursera or edX or Udemy. It's great that they democratize the access to content, and we're lucky to have access to content from Stanford and MIT sitting in India. But one thing that they have still not got to is the fact that every individual is different, right? And so, how can we personalize their journeys through content to maximize their learning? And so, what we built was an adaptive learning system that recommends content based on an understanding of how well does the student has consumed some content, understand that content, so that we can build upon that foundation and recommend other content to them, right? And of course, as you know, in education, there are lots of dependencies between different topics, right? So you can't understand machine learning if you don't have a solid foundation in probability theory. You're not a good programmer, and have a good solid foundation in topics such as linear algebra and calculus. So to take that into account and the dependencies between the topics during the recommendations systems execution is another very important aspect and a difficult aspect to deal with, right? And again, this is an example where we used actually a method called Bayesian graphical models rather than collaborative filtering or content-based filtering. We also have built a recommender system for a startup in the US that was looking to build a platform for trading of bonds, right? So financial instruments. And here, what the problem was that an organization that's trying to buy certain bonds that are not available in the market, can we recommend to them alternative bonds that meet their criteria, right? So what is their portfolio of bonds that they have right now? What's the bond they were looking for? Can we actually come up with a recommendation? So this was kind of content-based approach, but also kind of collaborative in that you're looking at a portfolio of bonds that you wanted to actually hold at any one time. So what is recommendation, right? And so let's get a little bit into the theory of it now. I'm not sure as to how much the audience has been exposed to machine learning, but essentially when we talk about machine learning, which is a part of AI, we're basically saying that there must be some data, right? And from that data, we want to learn a function that in some way approximates a real world process, right? So the real world process may be matching or recruitment, right? As we will see as one example. So the real world process is generating some data. What is that data going to be? It's going to be features associated with the JD, the job description. It may have the CV of a particular candidate, and then was the candidate shortlisted, right? So we have some kind of a label given here which says shortlisted, yes, right? And so what we want to learn now is we don't know what the real world process was that actually labeled the candidate as being shortlisted or not shortlisted for a job description, but we have this data here. And we are basically trying to approximate this function that exists in the minds of the humans who are actually doing the shortlisting. And we're trying to learn something that says, okay, give me a JD and give me a CV or a resume of a person, and I'm going to map it onto whether yes or no for whether they get shortlisted. Okay, and that's what machine learning basically does. And of course, recommender systems is also a part of machine learning, and so we have some data. But what's the data we have here? We have a user J, that has rated an item K from the set of all items I, and has given it a rating RJK that is in the range of, for example, a 5-star rating that we might be giving movies, right? Or, 5-star rating we might be giving to a product that we've bought from a retailer. And so I say, the rating has to be in the range of, values here. I'm assuming there are integers and R here typically would be 5, but of course we could choose a rating scale of 7 or 10 or whatever. But 5 is the most common rating scale. And what we are trying to do here is learn this function f that given a user, any user, and any item can predict what the rating of that item would be by this user. Okay, so that's the problem that we are trying to solve. Now, how machine learning solves that problem is we define a cost function. And this is essentially a function that measures the error in our prediction. And it tweaks the parameters of this function to minimize this cost function, right? And in our case, because this is what is called a regression problem, we typically use something called a mean squared error, where we are saying that essentially in the data set that we are learning the function or approximating the function from, we have certain ratings. For those ratings that exist in our data, we want to compare it with what our function is predicting, and we're taking the square of that difference and taking the average here, right? So we are taking the average error in prediction when we use this function f of known ratings given by users to items, right? And just so that for those of you who have not come across machine learning in any great detail, this is essentially what we call the regression problem. So what are we really saying here? So our data set looks like a matrix. You have rows that represent users, right? So here we have user UK, and we have columns that represent items. Here we have item IJ. And at the cross section of this column and this user, we have the rating given by user K to item IJ. Okay, now one quality of this data is that this is very sparse. What do we mean by sparse? What we are saying is we have a lot of missing data in this matrix, right? Because if you think about any user, typically a user would rate less than 1% of items, right? So of all the cells that are available here in this row, we only have ratings in less than 1% of the cells. The rest of the cells are empty, right? And so it's a difficult problem to solve. And the difficulty comes from the fact that you have a lot of sparseness within this matrix. Now, one of the things that we have to remember is, of course, that a user that is consuming, and let's keep with the example of movies. It was one of the early domains that was addressed by recommender systems. These ratings are not given in a bubble, right? There's a reason why that rating is given, and that reason we would call preferences. So every user has certain preferences. So this user, for example, may be interested in movies that have great cinematography or special effects. They might be interested in a particular production house like Dharma, may be interested in some genre, or maybe fans of a particular movie star, right? And so based on that, they are giving ratings. Now, of course, asking users for data is actually really, really difficult on the web. Or in general, right? Nobody is really happy to spend lots of time explaining why they gave a rating. Now, there are reviews that are given by some people, but that's a very small percentage of people who actually consume items. So it's a lot better or easier to just get a rating than to get a detailed review of that particular movie from this user. So these are typically what are called hidden variables. Right? They are in the mind of the user, but are not given to us. So they don't exist within our data. Now, so let's look at an example here. Essentially, we have an example where we have 7 users here. So each row is a user, right? And we have a very simplistic case where we have 6 movies. And the ratings here we are assuming are continuous scales. So you can see a rating of 2.5, for example, given by Michelle to Titanic. Now, the active user here is Chan. And we can see that Chan has given a 4.5 to Batman, 4 to Superman, and one to Spider-Man, the question is, do we actually recommend The Matrix or Inception or Titanic to this user, right? And like I said, the way that we actually will approach this problem in what is called user-based collaborative filtering is that we would say, okay, a user is described in this n dimensional vector, right, where n is the number of movies. And using this vector representation, which is the ratings given by users to some subset of movies, we are going to try and find people who have similar interests, right, by looking at all of these users. So essentially what we are saying is Chan has given a 4.5 to Batman and a 4 to Superman, and Chan did not like Spider-Man, right? So if we are looking for somebody similar to this profile, well, Tom seems to have a pretty good profile here, right? So has given a 4 to Batman, a 3 to Superman, and has given a negative rating to Spider-Man as well, right? And so we are trying to find users that have given similar ratings to the same movies as those rated by Chan, and that defines, as I was saying earlier, the neighborhood. Now, what complicates the issue further is the fact that you may have a context, right? So typically when we talk about context, we talk about the location of a person, or we talk about time. Well, of course, the context is much more complex than that, right? So you add a couple of children who are watching the movie along with their dad or mother, and suddenly their preferences have changed, right? So now they want animation, they want Disney, they want Pixar, action heroes and comedies, right? Instead of what we had earlier, which was cinematography being important and so on, right? And so the function that we are now trying to learn isn't a function that just takes a user and an item and gives it a rating. We now have a more complex function that has a user, an item, and a context. So it actually takes a triple and recommends this particular rating for a movie. Now, obviously, what this means is that we need the context to be defined. Now, in some cases, we may have the context actually explicitly given to us, the fact that we know the time of day that somebody actually watched this movie. In other cases, the context becomes also a hidden variable, right? So what you're now doing is you're trying to figure out based on, the kind of mix of movies, whether there are multiple contexts within which these movies were actually rated. And you're going to use that then in making your predictions. So, just to go through the process, then, user U4 here is our active user. And let's assume that U1, U2, U3, and U5 are, our neighborhood of UA. What I have here is pre-computed the similarity of U4 with each of these users. And so obviously this is basically saying that U4 is going to be perfectly similar to itself. So the similarity goes between 0 and 1. And typically what we use here is cosine similarity. So again, for those of you who've never come across this term, essentially what we are saying is that we have two vectors in some high dimensional space. We are looking to identify how similar these two vectors are based on the cosine of the angle between these two vectors. And what that really comes down to is the cos of theta is essentially the ui dot uj, right? So it's the dot product of the vectors divided by their length. So essentially what we've done is we've pre-computed this, and you can see that the most similar user here is U3, and you can see why, right? So U4 and U3 have actually rated these two movies in common and have given them decently high ratings. Now, what is interesting here, of course, is the fact that if we look at U2, you know, he's given a 3 here and a 3 here as well. So a little lower than what U4 has given, but has also given a negative rating to I6, which is in common with U4. And so in some ways you can see that U2 and U4 are actually even more similar than U3, right? But the cosine similarity calculation is suggesting it the other way around. But actually, what we can also see is that the average rating given by U2 is a little lower than the average rating given by U4. And so if you adjust for that, when U4 essentially gives a rating of 4, an equivalent rating by U2 is actually, right? And so you have to take into account that all of these ratings are crowdsourced. And so different people have different scales for the data rating that we gave, right? And so you have to adjust for this difference in rating scale. And as we can see, our proxy for rating scale is the average rating given by user. Okay? And so while I've talked about cosine similarity as being the standard approach for calculating similarity, there is something called the adjusted cosine, which actually adjusts for the differences in rating scales. And another way that we talk about this is the user bias, right? So what we can say is that user U2 is a hard rater compared to U4, right? So we come across that all the time. When you were in university, you'd have certain teachers that would just not give you very high marks, and they would be considered as hard markers, and others who would actually be quite happy to give you a full mark in an exam, right? And so the idea here is that you've got, now the idea of coming up with recommended ratings. What's happening here is for I4, we are taking the ratings that have been given by users within the neighborhood. So that's the 4, 3, and 2 that you can see here, the 4, 3, and 2. And you're taking a weighted average where the weight is actually the similarity, right? So we're actually taking this value, and this one here as weights, and we are multiplying them by the ratings given here. So users' ratings of users that have actually given a higher, that are more similar to the active user will give more weight to the prediction on what the rating of this particular user. Okay. Now, as I had mentioned earlier, there are a number of problems. We talked about the new item problem, which is also called the cold start problem, where a new item that comes along cannot be recommended. We also have the new user problem, which is a different kind of cold start, where a user has not consumed anything, and so there's no way for us to measure the accuracy of between users. And so in both these cases, we can't do any recommendation, right? And we fall back on things like just recommending the most popular items. It's a very impersonal approach, right? And of course, there are better ways of doing these things, but again, we won't have time to do this because we have limited time today. Other issues, related to new items, is the kind of idea of how do you measure the goodness of a recommender system. And of course, we could measure the goodness based on the accuracy of the recommended rating. But also another way of looking at it is that, what's the item latency? So if an item has been introduced to the market at time t0, what is the delay between when it was introduced to the market at time 0 and the time that it actually started getting recommended, right? And so that is one way to measure how good a recommender is. You want this delta to be as small as possible. Okay, so that's an issue. And then, of course, then sparsity of ratings is another issue here. So what we are saying here, as I mentioned earlier, is that typically these accuracies are being measured on very small number of items, right? So the similarity between U3 and U4 is only based on these two items, because even though they have rated other items, there aren't any items in common other items in common. So the similarity is based on a very small number of items, and that's not a great idea. Anybody who's done statistics would know that that's not a good idea. And then the other interesting piece is, should all items be treated equally? So, everybody loves Spider-Man. So, if I have given a high rating to Spider-Man and somebody else has given a high rating to Spider-Man, does that really mean that we are similar compared to if there was a, off the wall kind of movie that most people haven't seen? And if we have both given that a high rating, then surely that should contain more information than Spider-Man, being the common movie between us. So how do we actually deal with that is another area that the researchers looked at. In terms of the different types of algorithms, we've looked at user-based collaborative filtering, where for UK, we look at other users that are similar, and then we take their weighted average to come up with this prediction. An alternative to that is item-based collaborative filtering, where if we are wanting to see, what is the rating that UK is going to give to item IJ, then instead of looking at similar users, you can also look at similar items instead, right? And so what you're saying is that an item now is described as an n-dimensional vector based on ratings that have been given to the item across the user base. And we then calculate similarity between items and calculate this as a weighted sum of ratings given by UK to items that are similar to this particular target item that we are considering recommending to them, right? And so it's a similar philosophy, but rather than similar users, we're looking at similar items. Now, this is all good, but of course, it was treating ratings as individual objects that were rated almost in a bubble, right? We weren't looking at similarity between items in some way or statistically, correlated items. And so this idea came up of matrix factorization. And just as, in high school, we had learned that if you have, say, an integer 2 and 3, we can actually factorize that by saying, okay, the prime factors of this is 2 and 3. Multiplying the 2, you get 6. The same idea was used here, right? So this is our rating matrix, and as you can see, this rating matrix has a lot of missing values. So this is sparse matrix. The idea here is to say, well, maybe we can approximate these two matrices P and Q, where in some hidden dimension, I'm showing only 2 dimensions here, but actually in general, we could choose any number here. The idea being that these hidden dimensions actually represent our preferences, right? That we have talked about, that were in the head of the user that was giving these ratings. And so what we are saying is that P is a lower dimensional representation of Tim's interest in movies, but now the numbers here are telling you as to how important one preference is over another one. And similarly, Q represents every item in that same lower dimensional space, where the numbers that we put in here are going to represent how good is this movie at satisfying a user that has a preference for H1 or H2. Okay, and so what we are doing here now is we are saying, well, these two matrices, if we take the transpose of Q, right? So this is our M by N matrix, which is our rating matrix here. And this is an M by 2 matrix and an N by 2 matrix. So if we take the transpose of this matrix, we can multiply the two, and we will end up with P Q transpose being an M by N matrix. And so we want to fill in these numbers out here and here in such a way that we can get a good approximation of our rating matrix when we multiply these two matrices. Okay, and so if we look at the result here, we've run an algorithm for matrix factorization, and we now have got these numbers. How did we get these numbers? Just as we would in any machine learning problem. right? What we are saying is these were unknown, so these were our parameters. We wanted to fill it in such a way that we can minimize the error in the ratings that were observed. So look at this one here. This was the rating was 2. When we multiplied these two matrices, our predicted value was 2.1. So it's a small difference. Here it was 1. We are now getting 0.99 here, right? So again, a very small difference. We look at this one here. This is a 3. What we're getting here is a 3.18, right? So if we look at our cost function, which was the sum of squared error in the observed ratings and the actual ratings that were predicted, we can see that that cost function is going to have a low value, right? But what magic has happened by us doing this matrix factorization is where we had a missing value here, we now have a predicted value of 4.37. So if you were recommending a movie to 10, we would actually choose I5 because it has the highest predicted rating, and we would definitely not be predicting or recommending I6 or I1 that get predicted ratings of 1.01 and 2.1, right? And so you can see again other examples where for Paul, we would choose this movie here, which, as you can see here, we did not have a rating for, right? And we can see that this one and this one here have very low ratings associated. So how do we do this? Essentially, like I said, we are approximating our rating matrix by multiplying E and Q transpose. We are minimizing this function here, which is our sum of squared errors, and we are filling in these two matrices P and Q. We are estimating what the value should be inside there to achieve this prediction. And let's look at an example. So this is a data set, which is a benchmark data set for recommender systems for a very long time. This was actually collected by the group Lens group in Minnesota. And what you see here is that this was the data of ratings given by different users. User 1 gave a rating of 4 and a rating of 4 again to movies 1 and 3. Those movies was Toy Story and Grumpy Old Men. The 0 here represents the fact that there was no rating given, and we can see the predicted rating was 4.32. And what is that movie? It's Jumanji, right? So this would be a recommendation. And as you can see, while we have not used the genre in the calculation, we can see that the Jumanji genre is adventure, children, and fantasy, and we've got fantasy, children, and adventure in here. So without using the content, we've still been able to give a sensible recommendation. And what I've shown here is the cost function as we run our optimization algorithm, which is something called gradient descent. Which is incidentally also used by neural networks, right? So when we train neural networks, we're also using gradient descent. We're using the same principle here to come up with recommendations. Now, of course, life gets more complicated. We recognize the fact that we have a user bias, an item bias, and then interaction between a user and an item. So, for example, if the item was Star Wars, well, everybody likes Star Wars. So typically, you would give it a higher rating than any other movie. So what we're doing here is we're saying there must be some average rating that's given by a person to a movie. And then, because of the movie, we might rate it higher. And that's this item bias, which we're saying in the case of Star Wars is 0.8. The user has a bias, so Derek may be a harsh rater, and so we would actually reduce the rating now because of the fact that the user is Derek. And then because Derek actually liked Star Wars, then the contribution of this interaction term would be where we are adding a 0.5 here, right? So the overall rating for Star Wars by the user would be 3.4, which is the average rating, plus 0.8, which is the item bias, subtract from that the user bias, and add in the interaction term, right? and we get a 4.3. Now, all of these then become unknowns that we are trying to learn, and it just makes the maths a little more complicated. But essentially, we still have cost function that we are trying to optimize. And what we don't know is again the P and Q, but also we don't know the user bias and the item bias. So the number of parameters that we have to learn increases, and how we do that again is like gradients. Okay, I won't go into the details because again, I'm not sure as to how much of machine learning background work. Now, one of the interesting things that happened was a few years into this whole research, we came up with the Yahoo researchers in Yahoo Music started looking at this problem. What they found was that items, are rated by users under different circumstances in different ways, right? So if you actually brought a user in who was going to use your recommended system and said to them, hey, here are a set of random items, I want you to rate them based on whether you like them or not, you would end up with a distribution that looks like this, right? So a lot of items typically are not liked by users, and you get very few items that get a 4 out of 5. On the other hand, if you actually tell them to just remember some movies or some music that they have listened to and rate it, you get a very different set of ratings, right? You actually, the recall by humans is typically more biased towards things that they like. So they will remember movies that they enjoyed, or they remember music that they have enjoyed listening to. And so this distribution of ratings can be very different. Now, typically, when we actually collect ratings, what we are doing is this kind of data collection. So our data that we have in our rating matrix looks like this, but actually the data would look like this if we had done that random selection, right? So actually what this means is that there is what is called a selection bias in rating, and this causes problems for machine learning. And so again, I don't want to get into the details of this because I think this will take time and it also may not be completely central to what your interest area is. But essentially, we can use what we have learned there and create a similar algorithm that doesn't now consider predicting ratings as important as selecting a subset of items we call the top end recommendation. They actually choose a subset of items that are going to now be recommended to a user that have been selected from all of the items that they have now seen in the past. So that's one type of algorithm. So if we go on to then content-based filtering. So what we've talked about till now is collaborative filtering. Let's get into content-based filtering. So how does that work? Right? So, for example, a news website where a user comes along and reads this particular article. For those of you who are not Hindi readers, I apologize, but essentially this article is about some commotion between two communities in the city of Indore, and a central character there is a BJP MLA called Usha Thakur. So, the person who is reading this may be reading it because they're interested in the location more, and so they have an affinity to it. Maybe they come from there but are living in a different city or a different part of the world, so they're reading this article, right? So that's a different dimension to somebody who's a BJP supporter or Usha Thakur supporter. Or the person might actually be interested because they're a Muslim or a Hindu, the communities that were involved in this issue. Or it could just be any Indian that doesn't belong to Indore, doesn't actually belong to any of these communities, or is not a supporter of any political party, but is just generally worried about communal rhetoric in the country, right? And so again, what we have is that there are these hidden preferences, right, of why somebody likes the item that's being consumed. In this case, the item being consumed is not a movie, it's not something that you can buy, but it's actually a news article. Okay? And so what we really want to do is we can look at how long did they spend reading this news article, and based on that, we can derive some kind of a implicit rating. But we really, if we want to recommend the next article, should it be another article about Indore on a different topic? Should it be about Usha Thakur? Should it be about one of the communities or about communal tensions in another part of the country, right? And so that's what we are trying to solve here. But of course, this can be used in other areas also. So another project that we worked on is, in the education space, where this is a peer-to-peer learning platform that we've created, and we are recommending questions that have been asked by one user to other peers who are most likely to give a good answer to this question, right? Explain the issue that this particular user can't understand. So here, again, it's a content-based problem. We are looking at questions that have been asked and what have people successfully given answers to that have been right in the past, and we are trying to then recommend those questions. Of course, I talked about news, and we've built a news recommender as well, using the principles of what you're looking at here. Now, one of the first things that you do when you're dealing with text is you try and extract what are called named entities. Right, and so what you can see here, what do we mean by named entities? Things like communities or organizations, people, events, right, job titles, right? So we are trying to basically come up with tags for each of these things. Now, there are a lot of pre-trained models that are available that you can use to extract some of these, like location and person and organization. But you might have certain specific interests like events and jobs that are not covered by these named entity extraction models that are available. For example, there's one by Stanford, very popular. And so in that case, what you need to do is manually go through a bunch of data and tag it, right? Saying that this Bakrid is an event, Durga Puja is an event, right? Vidyaarthak is a job. Right, so we are actually going and tagging all this, and then we can use machine learning to learn that and extract these tags. So we understand that these are the key things within this article. Also, my favorite example here of how vocabulary is impacted by the individual who's writing the article. So if I am giving this talk on recommender systems and got Shashi Tharoor to come and give the same talk, the vocabulary he would use would be very different from mine, right? Because we all know the vocabulary is different from most human beings. Now, instead of looking at word similarity between articles, we can actually represent articles at a semantic level. Right? So we say semantic level is what is the article about, right? Rather than the syntactic level, which is what are the words used here. Right, so for those of you who are computer programmers, a similar case can be made if a program is written in Java and another program, the same program is written in Python, because the keywords might be different. If you just look at the words that are used in the program, which is a syntactic similarity, you will actually say, oh yeah, these two programs are completely different from each other. But if you had a way of representing what actually is the program written to achieve, right? So this program might be written in Java and Python, but it's doing the same thing. It's calculating, given an integer x, it's calculating the square root of x, right? So if we can actually in some way create a semantic representation, then we should be able to say, their syntax is different, but they are doing exactly the same. And so the same idea occurs here, where in text, what we are doing is we are representing, the articles in what is called topic space, right? And one of those topics may be controversial communal rhetoric, right? And so by identifying these topics automatically, we can now represent articles not just based on the words, but also at this topic level and compare them. So what we typically do when we create these news recommenders is that we take each article and we extract features, right? So this is an area where we what we call feature extraction, which is a representation of what is called unstructured data, which is the text. and we're converting it to a set of features, right? And now we have a user that may have consumed all of these articles, so we can take some form of summarization, right? Aggregation of these vectors of each of these articles and create what would be a user profile, right? And because the user profile has been created by, for example, taking the weighted average of all the article features that the user has consumed, now the user is represented in the same space as articles, right? So we can actually compare a user to a bunch of articles and make recommendations. And that on its own would be content-based filtering. But what we then said was, well, if we actually now have a way of representing a user based on the articles that he's consumed, and we know content-based filtering gives very narrow recommendations, so the articles will be very similar to previous articles that this person's consumed. Why not actually look at extracting a neighborhood of this user, right? So this is our active user UA. We now, because we have a common way to represent users, we can actually take the neighborhood and we can then take the average of the neighbor profiles with the user profiles and create what we call an enriched user profile. And now that we have an enriched user profile, what we are doing is we are using that and comparing it with these news articles, and we are now getting a hybrid recommendation, right? Because what we are doing here to create this enriched user profile is essentially collaborative filtering. Right? And if you look at what we ended up building as a recommender system here, is we calculated the average consumption pattern across the users. So that was, if you remember what I had shown you about when we were talking about collaborative filtering, there was the mean weighting. So this is the mean user. We are giving it a weight and adding that in to a weighted sum of the user profile. So this is the user bias, if you want to think about it as that. And this is the neighborhood profile, right? And we are combining these three things and coming up with recommendations. And why are we combining this? Essentially, this weight W2 will increase as the signal becomes stronger, right? So as a user consumes more and more articles, we can then identify a better neighborhood because we have a better representation of the user. And so W2 then goes up, which means that the effect of this average user goes down, right? And this way we are balancing what is typically in artificial intelligence known as exploitation versus exploration.
Hello.
So we are exploiting what we know about the user, but still exploring other areas that the user has not shown us an interest in as yet, because we are using the average profile. And we have then built recommenders in a similar way for fashion here. And this fashion piece was very interesting because we had customer registration data, we had purchasing behavior, so what items have they purchased, we had product features, so again this was going to be a hybrid recommender system. We also knew which clothes the user had actually viewed and not bought, right? So we were able to take all of these things into account, and we were also able to see, for example, whether items, by looking at the history of purchases of those items, are staple, that actually have a decent number of sales throughout the year, or whether they are seasonal, they have peaks during some parts of the year, or ephemeral, which was where they come for a short period of time and disappear and never get bought again, right? And so we were able to do some unsupervised learning and classify different items. We were also able to look at classifying users, right, based on users that buy items that are not bought by many people. So we say they have eclectic taste. We have fashionistas that buy an item when it's just come out and that becomes a really popular item. Or we have price sensitive people that are buying items that were very popular but buying it whenever they're on sale, right? And then these are followers that buy it only after it has become popular. So you have different types of users that can be identified. And this is another form of feature engineering that was done. Another form of feature engineering, which we use neural networks and deep learning for, was to identify. I'll take questions at the end. I'm almost at the end here, so you can just hold on. I'll answer all questions. We had images of dresses, right? And those images themselves, rather than using raw images, we extracted a set of features here. What kind of fit it is, what kind of style, what kind of neckline, and dimensions that I didn't even know existed before we actually started working on this project, because I didn't know a lot about ladies' fashion, right? And this is the fun about being a data scientist, because you get to get exposed to so many different domains as build solutions to. Another recommender system that we built was where we built an app for a US customer where you could take a photograph of your fridge and maybe your fruit and vegetable basket, and we would identify what you have in your fridge and in your kitchen and start recommending recipes that you could actually cook for your family. And of course, this has interesting applications or aspects to recommendation. Food is a very, is a group activity. Families and friends each together. So it brought around, ideas of group recommendation. Also, another thing that we explored here was this idea of conversational recommendation, where this is a snapshot of an early conversational recommender that recommends restaurants, where you say, I like this particular restaurant here, and it comes up with a recommendation, and you can critique it based on different dimensions, right? So whether it is too traditional or too expensive, or cuisine isn't right, and then it comes back with other recommendations. So this is something that is called critiquing and tweaking, or actually tweaking and critiquing, right? And so we brought that into here. Group recommendation, if you have a group of friends that want to watch a movie together, how do you recommend to them? Meal for a family, how do you create a solution that is least offensive to all of the members of the group? Another very important aspect that we haven't spent time on today is how do you create a diverse set of recommendations so that you are able to catch a signal from a user, right? So the first time a user comes along to your news recommendation site, how can you present them with the universe of news that you have so that they can look at that, and you don't have all Virat Kohli stories, right? Just because you believe that people are interested in cricket. So giving enough diversity in the recommendation is really, really important, and that's another aspect that we actually did implement within this solution. So, concluding very quickly, recommender systems has been, as you saw, the first collaborative filtering algorithms in the mid-90s. I was very lucky to get involved in this space in the late 1990s. So, have really seen it evolve over the years. There's some very interesting problems still to solve there. I talked about textual recommendation. I talked about recommending to groups rather than individuals. And of course, as we move to more conversational interfaces through chatbots, conversational recommenders where we can tweak and critique, right? So think about, if you were getting recommendations from your friend, you might say, hey, I want to go to a restaurant, what do you suggest? And, the friend knows something about you, so suggests a restaurant, and you look at the information about it, and you say, hey, this is too expensive, what do you, can you suggest something that's cheaper? And then the friend is going to take that critique and is going to change the recommendation, right? And so this is a very cool space that I think is going to become very important in the recommendation process. Okay, I'm going to stop here. Thank you for listening to me. And I hope this has kind of given you some ideas of what recommender systems are like, how they're built, and give you some exposure to the kind of examples of recommender systems And of course, if there are any questions, I'm happy to take them at this point. If you don't want to ask me questions right now because you're embarrassed about talking in front of 60 people, then you can also email me and I'll be happy to respond. Okay, so thank you very much for listening to me. Questions?
Thank you very much, sir. Let me moderate those questions for you.
Mhm.